In this video, we're going to solve more trigonometric integrals. So remember, this is not trigonometric substitution. This is trigonometric integrals, which are integrals that the integrand contains only trigonometric functions, either a single type of trigonometric function or some combination of trigonometric functions. All right, let's start by finding the indefinite integral of tangent x times secant cubed x dx. Okay, now the process we used to solve combinations of sines and cosines, the idea is similar for combinations of tangents and secants. However, the rules end up being a little different because the derivative of tangent and the derivative of secant aren't, it's like, okay, like for sines and cosines, the derivative of sine is cosine x, and the derivative of cosine is minus sine of x. It's not like that with secant and tangent. The derivative of tangent x is secant squared x. The derivative of secant x is secant x tangent x. And that's what makes working with combinations of tangents and secants different from combinations of sines and cosines. But the similarity is in the method. So the idea is, if you can separate the integral into a secant squared x dx, and then everything else is just some function of tangent, then you can make a u substitution, that u is equal to tangent x. Or if you can separate the integral into a secant x tangent x dx, and then write whatever is remaining as a function of just secant x, then you can make the u substitution that u is equal to secant x. But if you can't put the integral into either one of those forms, then we'll have to resort to another method. So if you've got some combination of tangent x and secant x, and you see that the power on the tangent x is odd, or the power on the secant x is even, then you can use one of those two methods. Here we see that the power on the tangent x is odd. And so if the power on the tangent x is odd, then you want to write it, you want to separate out a secant x tangent x. And so what we have is secant squared x, secant x tangent x dx. And then the power on the secant, it doesn't matter if it's odd or even. As long as the power on the tangent x is odd, then you can do this. Okay? And so sometimes we're going to want to use the trig identity, secant squared x minus tangent squared x is equal to 1. Why would we use that? Because the idea is, like, okay, we have secant x tangent x dx. We're going to be substituting that u is equal to secant x. But if we still had a tangent x, and we might have a tangent x, like, okay, the power on the tangent x needs to be odd, right? What if this was tangent cubed x? Well, then we'd be left with a tangent squared x. And so we need to, since we're making this substitution, we need to turn all of this that's separated from secant x tangent x, we need to turn that into a full function of secant. But we don't need to do that here because we've already got a full function of secant. So, all right, so du is equal to secant x tangent x dx. So, making the substitution, u squared du. There you go. So 1/3 u cubed plus c. So 1/3 secant cubed of x plus c. Okay, here we don't have some combination of secants and tangents. And unfortunately, it's not like with sines and cosines. We developed cookbook methods to solve even just like any power of sine on its own, any power of cosine on its own, the integral. We don't have a general methods for solving just a lone tangent power or a lone secant power. So in those cases, what we do is you just think about, okay, can you do integration by parts? Can you do a u substitution? But also, probably the biggest thing you want to do is you would take out your trig identities and just play with the trig identities. And so when it comes to tangents and secants, the main trig identity is secant squared of x minus tangent squared of x is equal to 1. And we're going to go ahead and make this substitution, and the reason why is going to be obvious. Because, well, okay, I'll tell you. The reason why is because when it comes to integrals, secant squared is much more preferable than tangent squared. Why is that? Because we know the derivative of tangent x is secant squared. So, let's see. Tangent squared of x is secant squared of x minus 1. So we've got secant squared x dx minus, okay, so this is just tangent x. That's it. Okay, so now, okay, we've got a power of tangent and a power of secant multiplied together. And to be able to use the cookbook method, you're either going to need to have an odd power of tangent, and it doesn't matter what the power of secant is, or an even power of secant, and it doesn't matter what the tangent is. Here we've got an even power of secant. And so in this case, we're going to want to separate out a secant squared x. So we've got tangent to the fourth x, secant to the fourth x, secant squared x dx. Okay. And then, so we're going to make the substitution that u is equal to tangent x, because then du is equal to secant squared x dx. But to do this, we have the secant squared x dx, but everything else needs to be a function of just tangent x. And to do that, we use the trig identity, secant squared x is equal to 1 plus tangent squared x. So tangent to the fourth of x, and then we've got 1 plus tangent squared of x squared, secant squared x dx. So now we can say that u is equal to tangent x, and therefore du is equal to secant squared x dx. So u to the fourth, 1 plus u squared squared du, like that. Okay, u to the fourth, 1 plus 2u squared plus u to the fourth, u to the fourth plus 2u to the sixth plus u to the eighth. Okay, so 1/5 u to the fifth plus 2/7 u to the seventh plus 1/9 u to the ninth. And there we go. So now we just substitute the tangent back in. So 1/5 tangent x to the fifth power plus 2/7 tangent x to the seventh power plus 1/9 tangent x to the ninth power. There we go. Plus c. Okay, so here we've got an odd power of tangent. And so what we do is we separate out a secant x tangent x. And then, but we're going to be doing the substitution that u is equal to secant x, since du dx of secant x is secant squared x. And so we need to change the tangent squared to a secant squared, a function of secant squared. The trig identity is secant squared x is 1 plus tangent squared x. So we got secant squared x minus 1 secant x tangent x dx. There we go. So u is equal to secant x, du is equal to secant x, tangent x dx. So u squared minus 1 du. That's simple. 1/3 u cubed plus u. 1/3 secant x cubed plus secant x plus c. Or no, this is minus here. I don't know why I put why I put plus. Okay, we have an even power of secant, and then it doesn't matter what the power on the tangent is. Now, if the power on the secant is odd and the power on the tangent is even, so we say, in this case, we separate out a secant squared x. Okay, then we want to make all of this a function of strictly tangent x. All right, so secant squared x is equal to 1 plus tangent squared x. So tangent cubed x, and then we've got 1 plus tangent squared x squared secant squared x dx. Okay, so u is equal to tangent x, du is equal to secant squared x dx. So we've got u cubed 1 plus u squared squared du. So u cubed 1 plus 2u squared plus u to the 4th du. So u cubed plus 2u to the 5th plus u to the 7th du. 1/4 u to the 4th plus 1/3 u to the 6th plus 1/8 u to the 8th. Okay, so 1/4 tangent of x to the 4th power plus 1/3 tangent of x to the 6th power plus 1/8 tangent of 8 tangent of x to the 8th power plus c. Okay, here we don't have like a cookbook method to solve this. If this was sine of the 5th of x or cosine of the 5th of x, we did, but there was no general rules we could use to solve like just a lone power of tangent or a lone power of secant. But the idea is what you're going to do is, for a problem like this where you don't have a exact method to follow from the start, we're just going to, you could consider integration by parts, but really what you're starting with is you're going to take out your trig identities and just try different trig identities, and what you're trying to do is get this into a form that you can then use that cookbook method. So what I mean is, okay, let's use the easiest trig substitution here. Tangent squared x is equal to secant squared x minus 1. And so by substituting this, we might be able to get either an integral or two integrals where one integral we can solve, because maybe it's like simple. And then the other one, it's a product of tangents and secants, but it's like an odd with a power for this on the secant that's even, or a power on the tangent that's odd, and we can solve that. Okay, so let's just replace one of the tangent squareds with this and see what happens. So we get tangent cubed of x, secant squared x minus 1 dx. See? And so with that, we get two separate integrals. Tangent cubed of x, secant squared x dx, minus tangent cubed of x dx. Okay, so looking at that, I mean, this actually did help a little bit, but let's go ahead and do this. Let's make this tangent x, and then we're left with tangent to the fourth of x, and so we can say secant squared x minus 1 squared dx. Well, I don't know if that helps either. So let's go back here. So tangent cubed of x, secant squared x minus 1 dx. So tangent cubed x, secant squared x dx minus the integral of tangent cubed x dx. So we can solve this, right? We have an odd power on the tangent. But what about tangent cubed x? To me, so tangent cubed x, we just do what we just did. We say tangent x, secant squared x minus 1. So we've got tangent x secant squared x dx minus, yeah, like that. Okay, so the textbook gives us the integral of tangent x. This is the natural log of the absolute value of secant x. Okay, here we say that u is equal to tangent x, so du is equal to secant squared x dx. So this is the integral of u du, 1/2 u squared. So 1/2 tangent squared of x. So this is 1/2 tangent squared of x, and then this is the natural log of the absolute value of secant x. Okay, so that is tangent cubed of x. So minus 1/2 tangent squared of x minus the natural log of the absolute value of secant x. Okay, so we just need to solve this. It's already in the right form. We just say u is equal to tangent x, therefore du is equal to secant squared x dx. So u cubed dx. 1/4 u to the fourth, so 1/4 tangent x to the fourth. So this is 1/4 tangent x to the fourth power. Okay, so minus there we go, plus c. Okay, and I want to let's check this answer. I'm looking at the answer key in the textbook answer key, and it's saying that this should be secant x to the fourth, but I think that both answers are correct. Let's take this derivative and see if we can get tangent to the fifth of x. So chain rule here. We've got, this is going to be tangent cubed of x, right? Bring down the 4, and times the derivative of tangent x is secant squared x. Okay, here we've got, this is going to be tangent x secant squared x. All right, the derivative of the natural log of something is 1 over that something times the derivative of that something, so secant x tangent x. And then plus c, the derivative of c is 0. So, all right, tangent cubed of x secant squared of x minus tangent of x secant squared x plus tangent x. Okay, so let's factor out a tangent x. We've got tangent squared of x secant squared of x minus secant squared of x plus 1. Okay, if we factor out a minus 1, we get minus tangent squared x secant squared x plus secant squared x minus 1. Secant squared x minus 1 is tangent squared of x. So tangent of x. So we've got tangent squared of x minus tangent squared of x secant squared of x. Let's factor out a tangent squared of x. So we've got tangent cubed of x. 1 minus secant squared of x. Oh, wait. We got a minus here. We factored out a, yeah. So now, if we factor out a minus 1 again, you've got tangent cubed of x, secant squared of x minus 1. Secant squared of x minus 1 is tangent squared of x. This is tangent to the 5th of x. So this is correct. I don't know where the textbook gets the secant to the 4th of x, but okay. All right, this is not of any of the forms that we worked in the textbook, right? We have like an x here, but again, the idea is, and you know, I guess I thought this wouldn't technically be defined as a trigonometric integral because I thought trigonometric integrals just had trig functions, but anyway, but the idea is you're thinking about the same principles that we learned when going through this section. The principles in the sense that we know that the derivative of secant x is secant x tangent x, but we don't have we don't have another, like we can't separate secant x tangent x out. Okay, so in that case, let's think about, is there a trig identity that we can condense this secant x tangent x down into something else? I don't think so. So let's just try integration by parts. And so integration by parts is, you know, you can use it for whatever, but think about what would we choose to be the u and the dv here. Well, we definitely want to choose the dv to be secant x tangent x dx because that's the simplest integral. Right? So we can say u is equal to x and dv is equal to secant x tangent x dx. So du is equal to dx and v is equal to secant x, right? So the integration by parts, u v minus the integral of v du. Okay, and the textbook gives us the integral of secant x. It's natural log of the absolute value of secant x plus tangent x. There we go, plus c.